Hello everyone, welcome to the 13th lecture in this series. With this lecture we are going to study about stacks, and of course with the previous lecture we learned how to implement stack ADT using arrays. With this lecture we are going to explore how the same stack abstract data type could be implemented using linked list representation. In one of the earlier lectures, we have already thoroughly explored the data structure named linked list. We have seen how to implement all the operations, namely insertion, deletion, search, modify, etc. with a linked list, and we of course explored the various types of linked list like single, double, and circular. And in specific for stack ADT's implementation, we are going to fix single linked list for our implementation. So let's dive down into how to implement stack using linked list. So here in order to implement a stack using linked list, first and foremost we may have to set up a single linked list. And you know, with the single linked list we mean it is a collection of nodes, and every node is supposed to have some value with it, and it will also have a pointer variable holding the address of the next element in the list. So here stack is going to be the same. The definition for the stack is the same. It is a list where we are going to do insertion and deletion at the same position, that is pointed to by top. Now just we are focusing on stack implementation using single linked list, and so let us imagine that we have a single linked list and we have a pointer named first to point to the first element in that single linked list. So here instead of first we will be using the pointer named top. So always the topmost element will be pointed to by the pointer named top, that is the first element is now pointed to by top, and we are going to add new element as well as delete an element at the same position, that is the first position in the list. So whatever we have learnt earlier with single linked list as insertion at front and deletion at first, that is going to be the rule which we are going to follow for performing push and pop operation on stack implementation using linked list. So here you could see a pointer variable named top points to the start of the list, and always we consider the first element of the list to be the topmost element in the stack. So here let us see this example. Here we have a stack with 3 elements 10, 45 and 8, and 10 being the topmost element of the stack. And if suppose we witness this as a linked list, then this should be the way the elements are placed. So here you see the linked list has 3 nodes, and the first node has a value of 10 and it is the topmost element, and so the pointer top points to it, and the first node has an address of 4500, which is of course the address of the second element in the list, and it has a value of 45 and it has an address of 7000, which is of course the address of the third element in the stack or the list now. So it has a value of 8, and you see its address is null, which means that marks the bottommost element of the stack in our case. So this is how we visualize or we try to implement a stack using linked list. So it is just a single linked list where we do insertion and deletion operations at the first position, and of course we just retain the pointer named head as we do always with linked list. And here we see more about how to implement stack with linked list. So you know, push and pop are the 2 operations, and as I said before, we are going to do the same at the first position or the head position in the list. And if I do a push operation, that is like adding a new node to the first position of the list. So first I have to create or allocate memory for the new node, then I should make some pointer adjustments to place this new node at the first position in the list. And if suppose I think of pop operation on stack using linked list, then it means that I am just removing the first element from the list, and after that the second element should be the first element of the stack or the element that is being pointed to by top. And once I remove the element, then I have to free up the space that is being consumed by the element or the node, right. So, we will be using free of there. So, here when we think of implementation, it is very straightforward, just because we have already learnt how to implement single linked list and that too operations, namely insertion and deletion at all the 3 positions. So, for us push and pop can be implemented fairly easily, assuming that we have a reference pointer head which always points to the first node in our single linked list. So, just by keeping track of the head pointer itself, we can map the same with our top, and we can perform all these operations, namely insertion and deletion, quite easily. So, here we see how to implement a stack. So, we store the items in a stack in a linked list, and the top of the stack is the head node, and the bottom of the stack is nothing but the node whose address has a value of null. That is going to be the last node of the list, and that is going to be the bottommost element of the stack in our case. So, we push by adding a new node to the front of the list, and if suppose we want to do a pop, we will be removing the first node from the front of the list. So, in this example, as you see, we have 4 nodes and we have a pointer named top which points to the first node in the list, and as such every node, just as we studied earlier for single linked list, it has 2 fields, one for holding the value and other for holding the address of the next element. So, simply it is a single linked list. So, now we look at how the physical implementation of stack using linked list will be. So, the first example as I have shown in figure A, it is the conceptual representation of a stack. You could see all the elements being stacked one above the other, and we have a topmost element being pointed to by top. So, when we think of its physical implementation, you could see that just because the stack contains 5 elements, we have 5 nodes, and you could see all the nodes being linked, that is every node has the address of the next node, and you could see the bottommost element of the stack is being is being denoted by this node whose address is null, and you could see a pointer named top that points to the first node in the list. And in addition, we have maintained a variable named count. It is used to keep track of the count of elements in the stack at any point of time. So, if you want to have a implementation of this sort, then we should define our data structure this way. So, here we have 2 structures, one for denoting the head and another for denoting every node. So, the structure for denoting the node is same as what we have learned before, one portion for storing data, another portion named link for storing the address of the next element. So, this node structure is the same as we have learned before for single linked list. In addition, to visualize this sort of implementation, we have defined another structure named head that has 2 members, one is count and other one is top. Top being the pointer that is holding the topmost element of the stack, and count is a variable which keeps track of the count of elements available in a stack. So, whenever we do a push operation, we just increment count by 1. So, that is the purpose of putting a variable named count in the head. So, here with this example, we learn how the basic operations actually happen with the stack being implemented using linked list. So, initially we create a stack, and at the time the stack is empty, nothing is there, but the head portion contains two members. We had a structure named head, which has stack head, which contains two members count. So, the value of count is 0 initially, and top is pointing to a value of null, just because the stack is empty. Then I try to do a push operation. So, before doing the push operation, the stack is empty. Now, I add one element to the stack. So, the value is green. So, that is being added, and since it is the first element of the stack, its address is null, and you could see top is pointing to the first element, and as such one element is added to the stack now. So, the value of count is 1. Then once again I try to do a push operation. So, before doing push, count has a value of 1. Now, once again I am doing push, and so the value of count has been incremented by 2. So, now what should I do is I should make space or allocate memory for the new node, right, and I place a new value of blue on the node, and now what I should do is hereafter blue is going to be the topmost element of the stack. So, top should point to it, and I should create a link between the previous element, that is green, and the present element, which is blue. So, I should put the address of green on blue, right. So, thereby I create a link between blue and green, that is the first and the second nodes in this case. So, now I try to make a pop operation. So, before doing a pop operation, the status is that we have a stack with two elements, blue and green. Now, I do a pop. So, ultimately the topmost element is blue and it has to be removed, and so now the stack is just left with only one element, which is green, and top is pointing to it, and you could see that the value of count is also getting decremented by 1. So, this would be the status now, and at last you have the example where we make an attempt to destroy the stack. So, by the time I destroy, the stack is left with one element. So, the purpose of destroy is that I just clear the contents of the stack. So, now the stack is a list with just one element. So, we free up that element, and we ensure that the stack has become empty. So, that is the purpose of destroy. So, here just because we have used linked list for our implementation, we can add any number of elements to the stack merely by invoking a malloc function, and whenever we remove an element from the stack, we can free up the space occupied by the element, and thereby we conserve memory with implementing stacks using linked list. So, now we move on to how to implement stacks using linked list. So, we are going to see the same with some example and algorithm. So, let us first look at algorithm for creating a stack. So, first we have to so here in the algorithm what you see is that we go with the implementation where we have a linked list as well as we have a stack head. So, that the algorithm dictates the steps we want to have in order to implement stack head. So, first of all we allocate memory for the structure named stack head. So, it has two members, as you know, one is count and another one is top. So, initially count is set to 0, top has to be assigned a value of null, and finally we return stack head. So, this is actually optional. If suppose you want to have stack separate and stack head separate, then you could adopt this algorithm. Otherwise, it is sufficient that we just maintain a list and do all the operations straightforwardly there. So, now let us see the code associated for a straightforward implementation of stack using linked list. So, first we define a structure, we define the node structure here. We just named the structure as LIFO. It just has two members, one is a value of type integer and another one is a pointer named next, and it is a self-referential pointer. Hope by this time you know what self-referential pointer is. And then I give an alias name for this structure named LIFO, and so hereafter it is going to be called as stack. Now, I define a variable for this structure named stack, and it is a pointer variable. So, top is a pointer pointing to a structure of type stack, right. Now, we see the procedure for create. So, create, as you know, where we initialize the value for top. So, initially top should have a value of null, just because the stack is empty at this point of time. Now, let us see how to do a push operation on this stack. So, whenever we try to add a new element onto the stack, first and foremost we may have to allocate memory for the new node, and then we put up data into the new node, and then this new node has to be made as the topmost node, and we may have to do some pointer adjustments and add the address of the second node to this current top node, and finally we may have to increment the count by 1. So, the last statement is true only if we think of implementing stack using linked list along with having a structure named head. So, in this example, as you see, we have two elements with the stack initially, namely blue and green. So, count is 2 and top is pointing to blue. Now, we want to add a third element to this stack, which is red. So, as such, I create a memory for this new node, which I call by p new, and put up data there, and initially its address is null. So, now we think of adding this element onto the stack. So, it is simply insertion at first position in a single linked list. So, what we have to do is top is already containing the address of the first element earlier. So, earlier the first element was blue. So, we need to fetch this address and put up there in the newly created node. So, thereafter the newly created node's address will have the address to the node having a value of blue, and after that what should be done is that top should be made to point to the newly created node. So, we have the newly created node being pointed to by the pointer p new. So, hereafter we make an assignment that top is equal to p new. So, the top would be pointing to the newly created node. So, we have just made two pointer adjustments. One is that we put the address of the second element on the first node, and the second is that we put the address of the first node on the pointer named top. So, once we do these two pointer adjustments, now push operation is said to be successful. So, now let us see the same thing with this example code. So, we have push operation. It takes two arguments. One is the value of top and the element to be added. So, initially I allocate room for the new element. So, I invoke malloc and create memory for the new node, and this memory is being pointed to the pointer named new. So, then I check whether memory allocation has been successful or not. So, if new is equivalent to null, it means memory allocation had been unsuccessful. So, I say that insertion is not possible or stack is full. Some message could be printed here, and otherwise, which means allocation is successful, and so I put the element to be added in place of news value, and news next in the new node's address part I just put the value contained in top. So, new next is equal to star top, and the last assignment which I should make is that hereafter new should be the topmost element. So, I just add this statement, that is star top is equivalent to new. So, this helps us to do those two pointer adjustments. Last two steps does those pointer manipulations, and thereby the new element now becomes the topmost element of the stack. So, in order to do a pop operation, this is the algorithm we have. First and foremost, we have to check whether the stack is empty. If so, we cannot do deletion or popping operation from it. Otherwise, we take the data from the position pointer to by top, that is going to be our data out, and we make top to point to the second node in the stack, and we decrement count by 1. So, again this statement is valid only if we have maintained a separate structure named head, where we keep track of the count of variables in the stack. So, this is how pop should be done. So, we have the example to demonstrate the same. So, here in our case we have a stack with 3 elements, and that is how what denoted by count as 3, and top being pointing to the topmost element, which is red. Now, I want to do a pop operation. So, ultimately red has to be removed, and hereafter top should point to blue. So, in order to take the value of blue, it is actually in the first node's address spot. So, I should fetch up the value from the first node's address spot and assign that to top, and I should make this node to be pointed to by some other pointer, so that I can use the same pointer for free of function. So, in our case what we have done is that first of all I have fetched the address from the first node's next part, and that has been assigned to top. So, hereafter top would be pointing to blue, and also I make one more pointer named delete pointer to point to the node to be deleted. So, ultimately I can give this pointer as an argument for the free of function, and that would help us to free up the memory being occupied by this node, that is the first node of the stack. So, this is how we perform a pop operation. So, let us see with this code how the pop operation really works. So, here for pop we just take a stack's top as its argument. Now, I check whether top is null. If null, it means the stack is empty. I just print and exit. Otherwise, we have some elements in which we can do a deletion. So, I fetch the topmost value from the stack. You know, top is the pointer pointing to the first node in the list. I just fetch the value that is held in the first node. So, that is star top arrow value. So, the first node's value is put up in the variable named t. Then what I do is that I just set up a pointer named p to point to the pointer named set up a pointer named p to point to the same thing being pointed to by top. So, top is pointing to the first node. So, now I make p also to point to the first node. After that what I do is that I set up for top to point to the next node in the list, which is the node following the first node. So, top next is nothing but it has the address of the second node of the list. So, that is now set to the value of top now, and then I proceed with freeing up the space being pointed to by the pointer p. So, p is actually pointing to the first node of the list, and so its memory would be freed up, and finally we return. So, this is how we have to do pop operation on a stack using linked list representation. And just as we learnt the purpose of isEmpty and isFullOf with stack implementation using arrays, here the same functions can be written for linked list as well. So, we check whether for checking whether the stack is empty, we might have to check the position of top. If top is null, then this function would return a value of 1, otherwise it would return the value of 0. So, it is very simple and straightforward. And if in case we want to check if it is full, here as just because linked list implementation, there is no way we can reach the full state, just because linked list is a dynamic data structure. As and when we want to add more and more elements into the stack, we can very well do the same with the help of invoking this malloc function. So, we do not actually make a check of whether the stack is full or not when we think of implementing stack using linked list. When we do push operation on a linked list implementation of stack, we do not check whether the stack is full or not. We straight away allocate memory for the new node and just add it to the first position in the list. So, in this example we have program here which simply helps us to understand how stacks are implemented using linked list. So, first this definition we have already seen how to define node structure for stack. Here in the first line we just define two structures which are used to represent stack A and B, and then we invoke create a function with A and B. So, in our case the top will have a value assigned as null in both the stacks A and B. Then I add 3 elements to stack A, 10, 20 and 30, and top would be pointing to the topmost element, which is 30 in our case. Again I I push 2 elements onto stack named B. They are 100 and 5. So, 5 will be in the topmost element of the stack named B. So, same with the other example which we saw with the previous lecture. We do a delete operation on stacks A and B by invoking pop. So, ultimately 30 and 5 would be removed, and then I take the topmost element from B and popping the topmost element from B and adding it into A. So, 100 would be added up into the new stack named A, and once 2 pops are done to the stack named B, B is now empty. So, I make a check whether B is empty. In our case it is empty. So, this printf statement will get executed. So, this is how we just create a stack and visualize how the same could be implemented using linked list. So, these are some of the applications of stack. There are some straight or direct applications and some indirect applications. So, hope everyone might have been using web browsers. One of the contents of the stack will get one by one. That is one of the real time applications, and you could see in any text editor we have the feature of undo, right. So, when we do some operations with the text editor, all those operations would be put up in a stack, and we can undo the same just by doing a popping operation from the stack. And in JVM, the chain of function calls or method calls would also rely on stack. So, I will be explaining more about it when we study the applications of stack in detail, and validation of XML also we make use of stack. And in order to say some of the indirect applications, almost in most of the algorithms stack is being used as an auxiliary data structure, and in some of the data structures it is being used even as its component. So, these become its indirect applications. So, to summarize whatever we have learned so far, with this lecture we learned that stacks can be implemented using linked list. So, in order to implement a stack using linked list, first we have to create a single linked list. So, in a single linked list we have a pointer named head to point to the first node in the list. So, here the operations namely push and pop both have to be treated as insertion and deletion at the first position respectively. So, it is straightforward. In order to do a push operation, we actually create a new node and make the top pointer to point to it, and whatever node the top had pointed to before will be the address, will be in the address part of the first node of the list. So, we make those pointer adjustments just to add the new node and make top to point to it. And whenever we want to do a pop operation, now we make a revision of the top pointer there. So, the first node contains the address of the second. So, we make top to point to the second node, and we make some other pointer to point to the first node and free up the node being pointed to by the new pointer. And peak operation is just returning the value that is held in the first node in the list. So, top is pointing to the first node in our case, and whatever value held in the first node is the result of peak operation. And when we talk of advantages of implementing stack using linked list, the greatest advantage is that there is no upper limit on the size of stack. So, as and when we want have new elements onto the stack, we can very well do that, and we can claim that there is efficient usage of memory there, where when we implement stack using arrays, just because we should not enter into overflow situation, we may try to declare an array of huge size, and at times not all the spaces would be of use, and we may waste some of the spaces which we have allocated. Whereas when we think of implementing stack using linked list, there is not going to be any wastage of space, as we will allocate memory only when there is a need. And when we talk of disadvantages, just because linked list implementation relies on pointers, memory requirement would be slightly more than implementing stacks using arrays. And just because we use dynamic memory allocation, then it will be considered as slowing down the operations by a little. And the use case of stack implementation using linked list is that whenever the stack size is highly unpredictable, then in such scenarios we can very well go with implementing stacks using a linked list. So, as we have learnt how to implement stack using linked list, now let us have some questions to test our understanding of the concepts which we have learnt so far. The first question is that how is the top of stack represented in a linked list implementation? So, the top of the stack is going to be a pointer here, and to start with our implementation, top will have a value of null, otherwise it would be pointing to the first node in the linked list. The second question is what happens during a push operation in a stack implemented using linked list. So, whenever we do a push operation, first we have to allocate memory for the new node, then we have to take the address available at the pointer named top. So, that is going to be put up in the new node's address part, and thereafter the new node will be pointing to the node that was first earlier. And the third step is that we will make the pointer named top to point to the first node in the list. So, these are the three steps which we will do during a push operation. The third question is how do you check if the stack is empty in a linked list representation? So, it is very straightforward. So, at the time of starting our implementation, we initialized stack top to have a value of null. So, we make a check whether the top is null or not. If null, it implies that the stack is empty. The fourth question is what is the main advantage of using a linked list to implement a stack compared to an array? So, we very well know that a linked list is a dynamic data structure. So, when we are not sure of the size of the stack, when the size of the stack is unpredictable, then it is better that we go with linked list implementation of stack. And final question is what additional memory overhead does a linked list implementation of stack have compared to an array? So, just because linked list implementation use or relies on pointers, it is going to consume some extra memory, and other than that we will not have any other overhead. So, I hope with this you will be thorough with the concepts of how to implement stack using linked list.